Very well. 6.3, finding the volume by slicing. So suppose you have a solid object and your X ranges between A to B. Suppose you're making vertical cuts. Okay, let me just share the screen with you and look at the graph, see what's going on. So this is your object. X ranges between A to B. X starting from A, stopping at B. Suppose you have a vertical cut and you look at the cross section of this object, the intersection between this cut and your object, which is a cross section. Okay, this is a cross section and it has an area. So there is an area assigned to this piece of object by using this vertical cut. So if I just continue cutting, slicing this object, I can find these little areas, and eventually if I add them all together, I get the volume of this object. So how does it work? We are taking each of these small slices, areas, and we are just shifting this to the left, to the right. So we have delta X, difference in X values. We use delta X because these differences are very, very small. So after multiplying each of these areas by delta X, so you can find the volume of this small piece. And if you continue forming the rest of these slices, multiplying by their delta X's and add them together. So we're using sigma, remember Riemann sum, you're using sigma, adding these multiplications, these small volumes. It gives you the volume of your object. So this is the big picture, what's going on here. By taking small slices and multiplying them by their delta X's, and finally add them all together, you can define the volume of any object. So this is the just idea behind it. Remember that if you just take very small pieces, these delta X's are getting closer and closer to dx. And your sigma eventually transform into integral. So by taking the limit while n goes to infinity, we can define the integral of these areas a of x with respect to x, while x ranges between a to b. That's how we define the volume of any object. General slicing method. So we just learned that if we have a solid object which extends from A to B on x-axis, and the cross-section of the solid perpendicular to the x-axis has an area given by function a of x, then the volume of the object can be calculated using the integral of area function when x ranges between a to b. Let's take a look at one example, see what's going on here. how we applied this formula. Volume of a parabolic cube. So suppose R is the region in the first quadrant. It's bounded by the coordinate axis and the curve y equals to 1 minus x squared. A solid has a base R and cross sections through the solid perpendicular to the base and parallel to the y-axis. And those are squares. Question says find the volume of this solid. Okay, let us visualize this, see what's going on. In x, y plane, your y is equal to 1 minus x squared. Y is equal to 1 minus x squared. Okay, so remember that we are cutting our object. We have a square and the sides, and this is our object. This is a slice which is vertical with respect to the base. So your goal is to find this area and take the integral. What is this area? How to find this area? So think about it this way. Suppose you have a square. Suppose each side is equal to L. What's the area of this square? We all know that this area is L times L, L squared. Very well. So take a look at this length here. This is the length that has one intersection with the graph y equals to 1 minus x squared. Okay, so the length of this square y is equal to 1 minus x squared. So 1 minus x squared, 1 minus x squared, the area is equal to 1 minus x squared times 1 minus x squared. Your L is equal to 1 minus x squared. So the area L times L is equal to 1 minus x squared raised to 2. We're multiplying two sides since they are the same. We just raise it to 2 dx. Okay, taking the integral is easy. Here you just multiply 1 minus x squared by 1 minus x squared. You get 1 minus 2x squared plus 4x to the 4th. So as you know, the integral of 1 dx is x. The integral of 2x squared is 2/3 x cubed. And the integral of x to the 4th is, so all of these have dx, dx x to the 5th over 5. So if you look at this integral, the outcome is x minus 2/3 x cubed plus x to the 5th over 5. We don't care about 0 because all of these have x in them. If you plug in 0, the outcome is equal to 0. So just plug in 1, you get 1 minus 2/3 plus 1 over 5. Take common denominator between these, and then the outcome is equal to 8 over 15. In the first quadrant, x is positive, y is positive, and you have a function. This is your x, and this is your y. So what's your function? Y equals to 1 minus x squared. How do you graph this function? What are the intercepts of this function? So X-intercept, to find X-intercept, set y equal to 0. When y is 0, 1 minus x squared is equal to 0. So x squared is equal to 1, x is 1, or x is negative 1. Negative 1 is not acceptable for us. We know that this guy is in the first quadrant. So x is 1. So x ranges between 0 to 1. 0 to 1. Next page. Another example for you. Volume of acrylic hemisphere. So here you have a solid which has a base that is bounded by curves y equals to x squared and y equals to 2 minus x squared. Okay? Cross sections through the solid perpendicular to the base and parallel to the y-axis. Those are semicircular. Find the volume of the solid. Very well. Let's see what's going on here. One function is y equals to x squared. The other function is 2 minus x squared. So what's the intersection between these two functions? Set them equal to each other. X squared is equal to 2 minus x squared. So 2x squared is equal to 2. X squared is 1. So x is plus minus 1. Note that in the question, it doesn't give you any restriction on which quadrant or anything like that. It just says, hey, a solid has a base that is bounded between these two functions. The first function and the second function. So the intersection between these two functions ranges between -1 to 1. So the lower boundary is -1 and the upper boundary is going to be just 1. Okay, so what is the area? What is A of x? How do we find that? Take a look at the question. It says the cross sections are semicircular discs. So you know that those are semicircular discs. So what is the area here? First of all, the area of any circle is pi r squared. We need to figure out what r is, then form the integral. So in general, area of a circle is pi r squared. So area of a semicircle or semicircle is a half pi r squared. But what is r? So take a look at r. R is not fixed. So your r or radius has an intersection with the intersection of these two functions. Therefore, the difference between these two functions gives you the value for the r that ranges over those values. These values are variables. So your r is equal to so first of all, we need a coefficient. I'll explain why we need a coefficient here. The upper function, 2 minus r squared. So let me write this guy in bracket here. The upper function, your upper function, 2 minus x squared, minus your lower function, which is x squared. We have to multiply this by a half. Why is that? This is the area. We have half of the distance. It doesn't go through the whole. So we have to multiply our radius by a half. So our radius is going to be a half 2 minus 2x squared. Your r is equal to 1 minus x squared. Now that you have your r, you can easily form the area of this semicircular shape. So our area, which is a half pi r squared, is now pi over 2, and our r is 1 minus x squared raised to 2. Very well, we have the area. Now we can follow the volume formula. Volume is integral, a is -1, b is 1, and we found the area to be pi over 2, 1 minus x squared raised to 2 dx. Very well, let us write 1 minus x squared in expanded form, then do the algebra. So the volume is equal to 8 pi over 15. Guys, again, for the radius, why we multiplied by a half? Look at the distance between these two functions. 2 minus x squared minus x squared is the total distance. So we have to divide this distance by 2 to get the radius. Let us move on to the next page. The disk method. We now consider a specific type of solid known as solid of revolution. Suppose you have a continuous function. Suppose f is continuous. And suppose f is positive. It's above x-axis. X ranges between A to B inclusive. Now suppose R is the region bounded by the graph of function f, x-axis, and two lines x equals to A and x equals to B. So what do we have here? We have our function above x-axis, and you're looking at the area bounded between your function. We're just following the description here. Bounded between x equals to A, x equals to B, and x-axis. So of course we get a region here. Then we revolve R around x-axis. So we're taking this guy and we just revolve this guy around x-axis. We are forming a three-dimensional object. Our goal is to find the volume of this new solid. And we're going to use slicing method. This is called solid of. It turns out the area of a vertical slice or cross-section is pi r squared. But what is r? R lands on function f of x. So area is equal to pi f of x squared. We learned how the slicing method works and how we get a volume using the area of the cross section. Now we know that this area is nothing but pi f squared. So we have a nice formula. This method is called disk method. Know the name of this method. Pi f of x squared, x ranges between A to B. That's how you find the volume of the solid of revolution. So let us take a look at one example, see what's going on here. Region R is a region bounded by the curve f of x equals to x plus 1 squared, x-axis, and two lines, x equals to 0 and x equals to 2. So it seems like our boundaries are given, A and B. Very well. So if you graph your function, f of x is x plus 1 squared, x ranges between 0 to 2, and we're revolving this around x-axis. So cross sections are circular shapes. The area is pi r squared, and we know that r is equal to f of x. So we're going to use disk method. The volume of this solid is pi f of x squared, while the integral ranges between A to B. The integral pi 0 to 2. Your r is x plus 1 squared raised to 2. It's a common mistake. Students forget to raise the function to the second power. Your function has already exponent 2. Don't forget to raise it to the second exponent. That's how we get x plus 1 to the fourth. So to find this integral, you can use u sub. This is the integral of pi u to the fourth du, which is pi over 5 u to the fifth power, but u is x plus 1, so you get pi over 5 x plus 1 to the fifth power, and your x ranges between 0 to 2. So here you get pi over 5. If you plug in 2, you get 3 to the fifth, minus, when you plug in 0, you get 1 to the fifth, which is 1. After you simplify this, you get 242 pi over 5. Washer method. So I expect you to ask, hey professor, what if we have a region or area bounded between two functions? In this method, we only had one function. What do we do now? So, suppose you have two positive functions, f of x and g of x are above x-axis, y is positive, so these two functions are here. Then you look at the area, a region bounded between these two functions, and x equals to a, x equals to b. You're interested in finding the volume of the solid when you rotate this solid, revolve this solid around x-axis. What is the volume now? So here you have, this is a big picture. Here you have a circle. The upper circle is f of x. You have another circle inside this circle. The inner circle is g of x. So the radius is not 0 to f of x. The radius is between f of x and g of x. So what are we going to do? We're going to find the area of the inner circle, the area of the upper circle, and subtract them. So the larger area, this is the big picture here, minus the smaller area. So your area is equal to pi. Area is equal to pi, the smaller area and larger area, pi f of x squared minus pi g of x squared. This is your new area. So the formula to find the volume of the region, the volume of the solid that revolves around x-axis, bounded between two functions, f and g, xa, x equals to b, those vertical lines, is equal to integral pi f of x squared minus pi g of x squared, while x ranges between a to b. This method is called washer method. Okay, one example for you. We're going to use washer method to find the volume. You have two functions, f of x is square root of x, g of x is x squared, and X is bounded between 0 and 1. What is the volume of the solid that results when R is revolved around X-axis? So, as you can see, we have two functions here, square root of X and X squared. X starts at 0 and stops at 1. So this is your region, and you are revolving that region about X-axis. So this is washer method. Area is equal to pi f of X squared minus g of X squared. So the first function squared, square root of X raised to 2 minus the lower function is X squared. You raise X squared to the second power. So you get pi X minus X to the 4th. So this is your area. Now for the function, you have pi X minus X to the 4th inside the integral. So volume is equal to integral 0 to 1 of pi X minus X to the 4th. Pi is just a constant. You can write it in front of the integral. The integral of X is X squared over 2, and the integral of X to the 4th is X to the 5th over 5. Very well. Now you just plug in 1. You don't care about 0 because both of these have X values, X variables. So if you plug in 0, it's going to be 0. So just plug in 1 and simplify. The volume is equal to 3 pi over 10. Next page. So far we learned that how to find the volume when we're revolving the region around about X-axis. Now I expect you to ask, what if we revolve the region about Y-axis? Do we use the exact same formula? The answer is no. We have to make a little bit of change here. Why is that? First of all, your radius is now changing. So suppose you have this region here. If you revolve this around X-axis, you get this shape here. And this guy goes here. So the shape is like this. What if we revolve this around Y-axis? Of course, you get a different shape, different solid. This is y equals to f of x. This is y equals to g of x. First of all, we have to write each x in terms of y. We get new functions in terms of variable y. This is your new solid. So you're rotating this guy here, here. So first, convert your functions, write them in terms of y, then you have upper bound, lower bound on y-axis. And then you're taking the integral with respect to variable y. Example, which solid has greater volume? Okay, perfect. Let R be the region in the first quadrant, okay? Let us circle this one to make sure we don't forget about the first quadrant. Bounded between x equals to y to the third and x equals to 4y. Which is greater? The volume of the solid generated when R is revolved about x-axis or y-axis. So we're going to compare these two. Very well. First, let us find that the volume about y-axis. We revolve that region about y-axis. X equals to y cubed, x equals to 4y. First of all, the boundaries are not given. So let us set them equal to each other to find A and B. X is y cubed, x is 4y. Guys, since I'm rotating this guy, revolving this guy around y-axis, I need to have my y values. So y cubed equals to 4y. So let us subtract 4y, y cubed minus 4y equal to 0. Let us factor out y squared minus 4 equal to 0. So y is equal to 0, y is plus minus 4. Of course, we are in the first quadrant. Y cannot be negative, and this is 2, not 4. Cannot be negative 2. So your y is equal to positive 2. So we found the lower bound, upper bound, and we know the formula. The integral 0 to 2 pi upper function, lower function. If you don't know which one is upper function, which one is lower function, you can always put this in absolute value, and the final answer is always positive. Very well. So this is your linear function for y, and this is your cubic function, which is below the linear function when, let me set this, x equals to each other. If you look at x-axis or y-axis, you can actually see the linear function is above your function here, your third root function. This is y equals to x over 4, which is linear function, and the other one is y equals to the third root of x, which is below your linear function. So first function, upper function raised to 2, 4y squared, which is 16y squared, minus second function squared, y to the third, raised to 2, y to the 6th. Then we take the integral. The integral of 16 y squared is 16 over 3y cubed, minus the integral of y to the 6th is 1 over 7 y to the 7. Y ranges between 0 to 2, so let us plug in 2. We don't care about 0, both of these have y, so 0 make it 0. So after plugging 2, you get 512 pi divided by 21. Okay, now what if we revolve this around x-axis? So when you're revolving this around x-axis, first of all, you have two functions. Y is equal to the third root of x, and y is equal to x over 4. So we need to set these equal to each other. The third root of x equals to x over 4. To get rid of 3, we raise both sides to 3, so you get x equals to x cubed divided by 64. So x cubed is equal to 64x. We subtract these two, you get x cubed minus 64x equal to 0. We can factor out x. You get x squared minus 64 equal to 0. So x is equal to 0, or x is 8, or x is minus 8. Remember that we are in the first quadrant, so x cannot be negative. Your lower bound is 0, your upper bound is b. Let us follow the formula in washer method, revolving about x-axis. So v is equal to the integral. X ranges between 0 and 8. You have pi upper function squared minus lower function squared. Again, if you don't know which function is the upper function, which function is the lower function, don't forget to use absolute value. So by looking at the graph, the upper function is the third root of x. The lower function is your linear function, x over 4. So the third root of x raised to 2. This is the third root of x squared, because the third root can be written as x to a third raised to 2, which is x to 2/3. So first function square is x to 2/3 minus second function square is x squared over 16. It's equal to 1 over 1 plus 2/3, x to 2/3 plus 1, which give you 5 over 3, x to 5/3. So if you flip this, you get 3 over 5, x to 5/3 minus the integral of x squared is a third, x to the third. 3 times 16 gives you 48. Now just plug in 8. 0, it just gives you 0. So forget about 0. So after plugging 8 and simplifying the whole thing, the volume is 128 pi divided by 15. So which number is bigger? Revolving about y-axis. Comparing this volume and the previous volume. So you don't get the exact same volume. Revolving about x-axis, revolving about y-axis give you different volumes. Last example. Okay. So suppose you have two functions, square root of x plus 1 and x squared plus 1. First of all, find the volume of the solid generated when the region are bounded by the graph of f and line y equals to 2 and the interval 0 to 1. Then you revolve this around line y equals to 2. Okay, perfect. Let's see what do we have. First of all, you have function f. Read the question carefully. It says graph of f. F is square root of x plus 1. Square root of x plus 1. So as you can see, we have to just shift the graph 1 unit upward because of 1. Then line y equals to 2. Y equals to 2. Then x ranges between 0 to 1. So this is your area. And you're rotating this, revolving this about line y equals to 2. About y equals to 2. So what is the radius? The radius, this is your radius, is 2 minus the function. Radius is 2 minus the function. You're not revolving this around the y-axis. You are revolving this about y equals to 2, this guy here. So your radius is 2, this whole distance, minus this function. Very well. Now that we have the radius, we can easily find the volume. We know that x ranges between 0 and 1. We have pi, and we have 1 minus square root of x squared pi r squared. Perfect. 1 minus square root of x times 1 minus square root of x gives you 1 minus 2 square root of x plus x. The integral of 1 is x. The integral of 2, let me write it here, square root of x is x to a half. So this is 1 over 1 plus a half times x, 1 plus a half. So this is equal to 2/3 x to 3 over 2. And the integral of x is equal to x squared over 2. So this guy is equal to pi, parentheses, x minus, you have a 2 in front of 2/3, 4/3, x to 3/2 plus x squared over 2, and x ranges between 0 to 1. So just plug in 1 here, 1 minus 4/3 plus a half times pi gives you pi over 6. B says, find the volume of the region R sub 2 bounded by the graph of G and graph of F on intervals 0 to 1, and it's revolved about y equals to -1. Okay. Now we're working with two functions, square root of x plus 1 and x squared plus 1. And we want to find the volume when we just revolve this about y equals to -1. Very well. First of all, we have to use washer method because we have two functions. And we have to make a little bit of change here because our y is equal to -1. So you're actually shifting these functions. Upper function, square root of x plus 1, a shift. Minus 1 gives you square root of x plus 2. For the second function, you have the same thing. X squared plus 1 minus -1, which gives you x squared plus 2. Very well. Washer method says we have the integral 0 to 1 pi, the outside function squared minus the inside function squared. You write each of these in expanded form, simplify, and take the integral. And finally, find the volume of solid generated when the region R2 bounded by the graphs of f and g, okay, on interval 0 to 1, which is revolved about line x equals to 2. X equals to 2. So take a look at your graph. This is your graph. Now you are revolving this about x equals to 2. Note that, guys, in B, x-axis is the same as y equal to 0. Here you have a vertical line parallel to your y-axis. So you are revolving this. Intuitively, you are shifting this and then revolving this around y-axis. So first of all, we have to rewrite our functions. One function was y equals to square root of x plus 1. The other function was y equals to x squared plus 1. Now you're making changes to your x. X is now 2. So x is equal to, if you want to take this one, square root of x is equal to y minus 1, and here you have x squared equals to y minus 1. So your first function is now x equals to y minus 1 squared to get rid of square root. And the second function is now x equals to square root of y minus 1. We are rotating this about a line parallel to y-axis. So we have to have all of these functions written in y, not x. Very well. Now we are making changes to the radius. We are shifting these to the right-hand side. So the radius of your disk is going to be 2 minus this function and 2 minus this function. The distance is changing, so your radius is changing. 2 minus y minus 1 squared and 2 minus square root of y minus 1. Now that you have your radius, the rest is easy.